Hi and welcome. This video is the fourth and final part in a video series on C# generics. The C# generics video series is the fifth part of a course on advanced C# concepts. In this video, we are going to first look at how, in terms of generics, the Msil code, or Microsoft Intermediate Language Code, is handled by the Common Language Runtime under the hood, as it were. If you stick around till the end, I'll show you how a utility that ships with Visual Studio for Windows, named Intermediate Language Disassembler, can be used to disassemble an assembly, whereby the Msil code can be extracted from the .NET assembly and inspected. We'll then look at a basic code example whereby the factory design pattern is implemented and generics is applied to our factory class so that this class can be reused to instantiate multiple types. We'll apply multiple constraints to our factory class to enforce design rules driven by the requirement for our code example. For more videos on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future releases from this channel. So let's briefly look at how generics in the Msil code, or Microsoft Intermediate Language Code, is handled by the Common Language Runtime. I'm not going to go into a lot of detail in this regard, but please check out this Microsoft document for a more detailed description regarding how generics is handled by the .NET Runtime. This document explains how generics is handled differently for value types and reference types by the .NET Runtime. Let's look at a few excerpts from this document. Specialized generic types are created one time for each unique value type that is used as a parameter. This means conversions are no longer necessary because each specialized generic class natively contains the value type. Generics work somewhat differently for reference types. The first time a generic type is constructed with any reference type, the runtime creates a specialized generic type with object references substituted for the parameters in the Msil. Then, every time that a constructed type is instantiated with a reference type as its parameter, regardless of what type it is, the runtime reuses the previously created specialized version of the generic type. This is possible because all references are the same size. Because the number of reference types can vary wildly from program to program, the C# implementation of generics greatly reduces the amount of code by reducing to 1 the number of specialized classes created by the compiler for generic classes of reference types. So, two benefits are highlighted in this document with regards to value types and reference types in terms of generics. Conversions are no longer necessary because each specialized generic class natively contains the value type. Generics greatly reduces the amount of code by reducing to 1 the number of specialized classes created by the compiler for generic classes of reference types. My goal here was only to draw your attention to the extra information regarding how the .NET Runtime implements generics in C# under the hood, as it were. Please read this document to gain a better understanding in this regard. So let's implement our code example where we'll implement the factory design pattern and use generics so that the object instantiation code is abstracted and can be used to instantiate multiple types. We'll use multiple constraints appropriate to our requirement so that special rules at compile time are enforced. Let's create a .NET Core console app and let's name it Digital Product Inventory Application. So in this very basic example, we're going to create classes for representing specific types of digital products. We'll also create classes for encapsulating data associated with the various categories of digital products. We are going to create a factory class used to abstract and centralize the construction of these different types into objects. We'll then copy code from a GitHub repository, and this code will serve as the calling client code. This client code includes a link query used to compile a report containing digital product information and their associated digital product category information. Code is also included to output the results of this link query to the console screen. This example is more about understanding the application of generics than understanding link. Please don't worry if you don't fully understand the link aspect of this tutorial. Link will be discussed in detail in upcoming tutorials. So let's create our factory class. This tutorial is not about design patterns, but the factory design pattern is used in this example as a device to show how generics and constraints can be implemented to abstract the construction of objects of varying types. Special rules will also be applied through the use of constraints. Let's name this class factory pattern. So this class contains two generic types. So let's include the constraints for the type T parameter in our definition of the factory pattern class. As we know from our previous tutorials, constraints enforce compile time rules on our type parameters. So this constraint is enforcing a compile time rule that type T must be a reference type denoted by the class constraint, must inherit from type U, i.e. the other generic type parameter, and the type T argument must also contain a public parameterless constructor. This is denoted by the new constraint. Note that when the new constraint is used with other constraints, the new constraint must be specified last. In our code, we are going to instantiate an object of type T. Note that a generic type cannot be instantiated if the new constraint is not specified for the type that must be instantiated. We'll prove this in a bit. So let's also add a constraint to our uType parameter. We can do this by including another where keyword, followed by the relevant constraint or constraints for the U data type. Note that this class constraint for this example is in fact redundant for the U parameter, and I will remove this from the relevant GitHub repository. I'm applying this constraint at this point in the tutorial to show how we are able to apply constraints to multiple type parameters. So let's add a method to our class and name it getInstance. So the code logic for this method is instantiating an object of type T, which is derived from type U. The instantiated object is then returned to the calling code. So now, just to show you that we cannot instantiate an object of type T unless the new constraint has been appropriately applied to the relevant class definition, let's comment out the new constraint. And you can see that the C# compiler immediately complains. We must ensure that we have appropriately applied the new constraint in order to be able to create an instance of type T. So let's now create an interface named iPrimaryProperties. Let's add two property definitions to our interface, ID as int and title as string. So now let's go back to the factory pattern class. Let's add a constraint to enforce a rule that type U must implement the iPrimaryProperties interface. So we can do this by adding a constraint like this. Remember, the class constraint can be removed from the uType parameter. The code will still work as expected with it there, but for this example, it is redundant. So let's add an abstract class named productBase that implements the iPrimaryProperties interface. Let's implement the properties defined in the iPrimaryProperties interface as auto-implemented properties. Let's create an abstract class named categoryBase that also implements the iPrimaryProperties interface. Let's extend the productBase class by adding an auto-implemented property named categoryID. The categoryID property will be included within our link query to join the data stored in a list containing objects of type categoryBase to relevant product objects stored in a list containing objects of type productBase. We'll look at the link query in a bit. Let's extend the categoryBase abstract class and add an auto-implemented property named description. So let's create our category classes. Let's create our digital product classes. So our category classes inherit from the category base abstract class, and our product classes inherit from the product base abstract class. Note that both the product base abstract class and the category base abstract class both implement the iPrimary properties interface. Notice I am extending these classes with additional properties just for demonstration purposes. These additional properties won't be used further than this in this example. So I'm going to create a class named ProductViewModel, and this class will be used as a template to centralize information from the product-related classes with information from their relevant category-related classes. So we want our calling code, which we'll copy from GitHub, to create several product objects and related category objects. Then using link, we'll return a collection of objects of type ProductViewModel to the calling code. This collection will be the result of a join operation, joining objects of type product base with the relevant objects of type category base. Link is not the focus of this tutorial, but I thought I'd include the link functionality to make our example more interesting. As stated earlier, we'll discuss link in detail in upcoming tutorials, so don't worry if you don't understand the link-related code. So I've already uploaded the code for this example to GitHub. So let's copy the code, which will serve as our calling client code, from the relevant GitHub repository, which can be found at this location. This URL has also been included below in the description. Let's copy all the code from within the program class like this. And let's select the main method within our program class in our code editors and paste the code we have copied from GitHub over the main method in our code editors like this. And you can see that we have red squiggly lines under our code relating to our generic lists. So to fix this, let's add a directive to the system.collections.generic namespace. And in our getProducts method, where we are executing a link query, we have a red squiggly line here. So to fix this, we need to add a directive to the system.link namespace. Great. So let's look at the calling client code we have just copied from GitHub. The add properties to product method encapsulates functionality to add values to the properties of an object of type product base. The add properties to category method encapsulates functionality to add values to the properties of an object of type category base. You can see that these methods are currently public methods, but they don't need to be public, so we can change these methods to private. I'll update the relevant GitHub repository with this change. You can see here that our link query is encapsulated in a method named getProducts. The link query is selecting all product-related objects in the products list and joining each product with its relevant category. Each product is joined to its relevant category through the category ID property. The result of the link query is a collection of objects of type ProductViewModel, which appropriately combines product information with relevant category information. As stated earlier, link will be discussed in detail in upcoming tutorials. So let's look at the code in the main method. So notice how the factory pattern generic class is being used to instantiate each object of type product base. For example, we are instantiating an object here which represents a digital book entitled The Old Man and the Sea. We are instantiating an object here representing a movie entitled Shawshank Redemption. The factory pattern generic class is then reused to instantiate several objects of type category base. For example, we are instantiating an object representing the category with the title of movie here, and we are instantiating an object representing the product category here with the title of music. So the factory pattern class has been implemented to abstract the object creation functionality for this code example. We have adapted the factory design pattern to our requirements by imposing rules on the instantiation process through the use of constraints. So in the main method, we are instantiating our product-related objects, appropriately adding values to the relevant object's properties, then adding the objects to a list of product-related objects. We are doing the same thing for our category-related objects. We are then appropriately amalgamating information from the product-related objects with relevant information from the category-related objects into an object of type product view model through the use of a link query. We are then looping through the items returned from the link query and writing each item's properties to the console screen. So let's run the code. Great. I want to draw your attention back to the constraints in our factory pattern class. Note that we have implemented a constraint that the U argument must implement the I primary properties interface. So if, for example, we were to comment out the code in our class definition for the category-based abstract class that indicates that this class implements the I primary properties interface, look at how the C# compiler responds. Note how the constraint imposes a rule at compile time that the U argument must implement the I primary properties interface. For more detailed information on constraints, please navigate to this URL. So we were discussing earlier how the .NET Runtime handles generics based on the MSIL code. We are able to examine the MSIL code for an assembly by using a utility like, for example, the IL disassembler utility. So now, if we wanted to look at the MSIL code for this project, we can use this utility. This utility ships with the Visual Studio for Windows IDE. So let's run our developer command prompt for Visual Studio. Let's make the directory where our target assembly file resides our current directory. We can then type the following command. This command generates a file containing the MSIL code within the directory of the relevant assembly. This is the MSIL code that resides within the target assembly, created when we built our C# project. So now we can open the file we have just created in a text editor like Notepad and look at the relevant MSIL code. Great! For more detail on the IL disassembler, please navigate to this URL. All URLs mentioned in this tutorial can be found below in the description. Lastly, if you are interested in reading about generics and reflection, please navigate to this URL. If you are interested in reading about generics and attributes, please navigate to this URL. Reflection can be used to inspect generic types in C# at runtime, and this will be discussed in later videos created on C# reflection. Generics used with attributes will be covered in future videos created on C# attributes. In this video series, we discussed that generics was introduced in C# version 2. We looked at why it is better to use a strongly typed generic list to store a collection of items rather than an array list for this purpose. We discussed the benefits of generics. Generic classes and methods combine reusability, type safety, and efficiency in a way that their non-generic counterparts cannot. We looked at how constraints can be applied to generic type parameters in order to enforce compile time rules on generic type parameters. We created a code example representing a warehouse management system. In this example, we used the built-in C# generic queue collection type to store objects representing various hardware items that enter the warehouse and are subsequently processed. Generic delegates and events were instrumental in this real-time monitoring system. Lastly, in this video, we briefly looked at how the Msil code, or Microsoft Intermediate Language Code, is used by the .NET Runtime to efficiently handle both value types and reference types in terms of generics. We also implemented a generic version of the factory design pattern in a basic code example to demonstrate how the use of multiple constraints can be applied to generic types in order to enforce special requirement-driven compile time rules. I hope you have enjoyed this video series on C# generics. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course welcome. The code created in this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Thank you and take care.